Hello everyone, sorry for the technical problems, especially sorry for Tobias. And let's go to start more 1 week PDE seminar of Dean. And sorry. And we'll start. It's a pleasure to introduce the Professor Tobias Ried that will talk to us on a variational problem related to the Cwikel-Lieb-Rozenblum and Lieb-Thirring inequalities. Thank you.
Well, thank you very much for the invitation. It's very nice to be here. And let me just directly go ahead. So this is going to be a talk on an older result on the relatively new and improved upper bound on the number of negative eigenvalues of Schrödinger operators, the so-called Cwikel-Lieb-Rozenblum inequality. And surprisingly, or maybe not surprisingly, the same variational problem that I will show you also appears in the Lieb-Thirring inequality, namely the inequality on the sum of eigenvalues, sum of negative eigenvalues of a Schrödinger operator. And the whole story about the Cwikel-Lieb-Rozenblum inequality, that was a joint work with Dirk Hundertmark-Kunstmann and Vugalter from Karlsruhe. And we actually got a very nice result there. But one thing was left open, namely the solution of this variational problem that we derived. You will see in a moment, it's quite an unusual, peculiar variational problem, but together with Carvalho Corso from at the time in Munich, now he's a postdoc in Stuttgart, we were able to solve this variational problem. And I want to give you a few hints on what's going on there. It has a very nice connection, and I think very deep connection that still has to be fully uncovered to maximal Fourier multiplier estimates in harmonic analysis. And we will actually see in the solution of this variational problem some very nice, relatively basic, I would say, but very nice complex analysis methods. So let me go straight ahead. And if you have any questions, please don't hesitate to ask me anytime. So the first part, and actually, can I use both Blackboard parts? Can I use both parts? Okay, great. So the first part will be briefly on the Cwikel-Lieb-Rozenblum bound, which is a bound on the number of negative eigenvalues for Schrödinger operators. And let me just write minus Laplace for the kinetic energy plus a potential V. So we want to estimate the number of negative eigenvalues, which quantum mechanically corresponds to the number of bound states of a quantum system, single body quantum system that is described by this kinetic energy living in this potential. But we don't want any estimate on the number of negative eigenvalues, but we want one which is semi-classically correct, so with the right semi-classical behavior. Now, what is the right semi-classical behavior? And let me just do a very simple computation what the semi-classical guess would be. Very naive counting argument, which basically uses that by the uncertainty principle, a quantum particle in units normalized where h bar is equal to 2 pi would just say that in phase space, this particle roughly occupies a volume of order 2 pi to the d. So the quantum particle occupies roughly 2 pi to the d in phase space. And then we can just count classically what is the volume of the allowed region of this particle. and divide by the cells of volume 2 pi to the d. And that gives us the classical guess of the number of bound states of the system, which now classically would have kinetic energy p squared and a potential v. And that would just be 1 over 2 pi to the d, maybe write 1 over 2 pi h bar to the d times, well, the phase space volume, where momentum, let me call it eta, plus the potential as a function of the position is less or equal 0. And that integrated over the phase space. Well, that's an integral that we can simply do. Namely, it's radial in the eta variable. You can go to polar coordinates, integrate out the eta variables, because they go from eta squared goes from 0 to v. Actually, you can easily see that only the negative part of v is important. So in the end, what you will get is the volume of the unit ball in v dimensions, say, divided by our semi-classical counting times the integral. Now only the x integral is left, and you can easily see that from the volume factor, you will end up with a v negative part of x to the d over 2 dx. So that would be our guess. And the Cwikel-Lieb-Rozenblum bound says that this is essentially correct up to a constant. Just write correct up to constant. More precisely, the following holds. And this is the theme that goes back to Cwikel, Rozenblum, and Lieb. It was first proved by Rozenblum in 72, or rather in the typical Russian style, announced in 72, with a full proof appearing in 76, independently by Lieb in 76 and by Cwikel in 77, with very different proofs. Lieb basically uses functional integral methods, and I will come back to that because he actually gets the best bound on the constant that I will introduce in a moment. Cwikel gets a constant, but it was always believed that the constant from Cwikel's method is relatively bad. You get a constant, but it's orders of magnitude off from what you would expect. Turns out that we were actually able, with Dirk, Per, and Semyon, to vastly improve his method, and now in dimensions d bigger or equal 5, really get better constants than Lieb. Only 3 and 4 dimensions are somehow still missing, and that's where much more work is going to be needed. And Rozenblum's proof is essentially very abstract and doesn't give any good control on the constant. So let me just briefly fix the notation here. This bound is a bound that can only hold in dimensions more than 3. They're relatively easy counterexamples in dimensions 1 and 2, going back to Simon. But as Rozenblum actually told me that the Russians did it earlier, so that can also be found in early works by Biermann. And a funny side remark, that's actually a homework exercise in one of the books of Landau and Lifshitz. So the physicists were an easy exercise. Okay, so it's only possible in dimensions d bigger or equal than 3. For the positive part of the potential, which doesn't really play much a role in the estimate, we sort of need minimal assumptions, namely that it's locally integrable on RD. The negative part, however, has to be in LD over 2 on RD. And then the statement is that then the number of negative eigenvalues, which I will just denote by n of minus Laplace plus v, is bounded by, so n of minus Laplace plus v is bounded by, well, exactly what we would guess semi-classically, this classical constant times negative part to the d over 2 dx, but decorated with a constant, which in this normalization is sort of relative to the semi-classical constant. Which begs the question, how much does quantum mechanics differ from the semi-classical guess? Codified somehow in the question, how big is this constant C0d? And let me just discuss it in 3 dimensions, where the best upper bound so far is due to Lieb in his 77 paper, who proves using Feynman-Katz formula or trace identities that this is bounded by 6.869. And from the fact that if you look at this inequality, especially in the case when n happens to be 0, then what does this tell us? Well, this tells us that minus Laplace plus v, the quadratic form of it, has to be non-negative. But that encodes a bound that is essentially Sobolev's inequality. So if you play around a bit, you can actually show that the Cwikel-Lieb-Rozenblum inequality, if you assume that it holds, it gives you a constant for Sobolev's inequality. But we know the optimal constant in Sobolev's inequality. And by playing around a bit, rearranging, you can get a lower bound on how big this constant here can be, how big this constant has to be from Sobolev's inequality. And it turns out that it's 8 over square root of 3 in 3 dimensions. And that is big or equal. I did the calculation for you, 4.618 and so on. So that's somehow the region where we are. It's actually conjectured that in 3 dimensions, this should be the optimal constant, but we are very, very far from, or at least I would say we're very, very far from reaching this point. As I said, even with our new proof, we don't even get to Lieb's constant in 3 dimensions, but yeah, we stay around roughly 0.4 away, 0.3, 0.4 away. But that's sort of to give you a feeling of what is known at the moment. So let me quickly write down the theorem, our new bound, and I will not be able to show you the proof, but I will just introduce the variational problem that is encoded in this upper bound, and that's now our result from 22 that, to our great joy, we were able to publish in Invenciones, is that this C0d is bounded from above by a dimensional constant, which I don't want to worry much about, times a constant md. And this md, let me actually introduce a broader class of variational problems indexed by gamma. So here, gamma will be d, and in general, this gamma should be bigger than 2 in the following. So this starts for integers at 3, so that's fine. That is the following number. You take your favorite function m on R, which you think of sort of a cutoff function interpolating between 0 and 1. You split this function, and that's where things already get interesting. You split it by convolution into 2 functions that are in L2. And of course, this picture of a cutoff function is not really justified anymore because the convolution of 2 L2 functions has to be a function that vanishes at infinity. But that's just the outcome of the whole procedure. So you take your favorite 2 functions, M1 and M2, in L2 on the real line. take the product of their L2 norms, the whole thing to the power gamma minus 2, so that's always a positive power. And then you look at the convolution and see how much it deviates from the function e to the x. And you do this in L2, well, not quite. You do this in a weighted version of L2 in an exponentially weighted L2 space. So this L2 gamma norm of a function m, I will just define as the integral over r of m of x squared e to the minus gamma x dx. And if you can solve this variational problem, you get somehow the best upper bound on the Cwikel-Lieb-Rozenblum inequality, on the constant in the Cwikel-Lieb-Rozenblum inequality that is achievable by the method that we proved in this paper. So a few remarks are in order here. The main point that I want to make is that the proof, and that is really the main achievement in this work, highlights a very nice connection, interesting connection between bounds on the number of singular values. And that's now, for those of you who know it, the Billmann-Schwinger principle. You can reformulate this question here on number of negative eigenvalues of minus Laplace plus v in terms of the number of singular values of the Billmann-Schwinger operator, which are bigger or equal 1. And that leads naturally to the study of a class of operators, which is of the type f of the position, so f of x times g of momentum, so function of momentum in the sense of a Fourier multiplier. So, and there's really a nice connection between estimates on the number of singular values of the operator f of x times g of p, where here in our example, g would be 1 over the modulus and f would be the square root of the potential. So in our case, g of eta is 1 over modulus eta, f of x is square root of v, actually the negative part of x. So connection between the question of the number of singular values of this guy here, bigger or equal 1, and bounds on maximal Fourier multipliers. In the sense that this m here, this convolution, essentially induces a splitting of f of x times g of p into large and small values. If you think of the function m to take values between 1 and, okay, actually here I should say yeah, you think of m as sort of the identity, as good splitting of the identity. And a good way, and that's sort of one way to read this result, a good way of splitting it that is compatible with this question of number of singular values is actually given by such a convolution structure. So you take the splitting, and then you essentially end up with a way of splitting this product here into large and small values. And you can count them differently. One, you count in a Hilbert-Schmidt sense. And the good thing is about Hilbert-Schmidt, you can always calculate the Hilbert-Schmidt norm easily of such a product here. And the rest. And for the rest, you somehow have to be as robust as possible. And the best way of handling this is sort of going to sort of the supremum over all possible choices of how bad this function f and g can be. That naturally leads you to the concept of maximal operators. And since this here is a special kind of maximal operator, namely Fourier multiplication operator, you sort of are led naturally to the study of these maximal Fourier multipliers. And if there's time in the end, I will maybe write down sort of a core theorem of that leads to this bound. But let me maybe spend a bit more time on a very recent result with Thiago, namely that we are now actually in the position of solving this variational problem. And I think that's a really interesting piece of mathematics because you have several problems here in this variational problem. First of all, you take two functions in L2. You want to take the convolution. That's a highly non-local operation. So this is going to be very sensitive towards changes in either of the functions. And then you want both of them to be in L2. So the convolution has to decay at infinity. But at the same time, in a weighted L2 space, you want to make it as close as possible to the exponential. And it took us really a long time to get any grip on that. And I will show you that it has much to do with nice but very basic complex analysis. There's also some convex analysis involved, but let me maybe make some space, or actually now is a good time for questions on this part, because then I will do some more analytical things.
So I understand that you can estimate on this constant from dimension 3, 4, 5, and so on, and calculate it by taking some special test functions, MD, bound MD, right?
Exactly. So far what we did is really trying to find good test functions, but actually now I can tell you what the optimizer has to be. In an indirect way, because it will be best described in a sort of dual formulation, but you can actually write down an analytic formula for the optimizer here. But yes, and it turns out that in d is equal to 3 dimensions, the constant we can achieve now with really writing down the optimizer is 7.51 something. So that's how good we can get with this method. But it's, I would say, the first improvement that people have really seen in this, how small can this constant be business in the last decade. Yes, that's true, but yes, but this MD compensates for it.
How does it determine the dimension?
Because you have somehow here the L2 norm, product of L2 norms to the power d minus 2.
Oh, okay.
So I have to read this for gamma is equal to d. And with relatively simple test functions, but again, now we can really study the asymptotics precisely. You can show that for d going to infinity, this actually converges to a constant. This constant here does not converge to 1, no.
This is not so surprising.
Yes, yeah.
So MD doesn't, MD is just bound. If you say that this goes to a constant.
Yeah, you have to modify a little bit with polynomials in D. I can show you later if you like. But yeah, in principle, yes, it's not too surprising. That's also one of the benefits of the proof, because all the previous proofs actually gave you a constant or bound on the constant which grew in the dimension. Also, Lieb's proof sort of gives you something that grows like square root of the dimension. Here you immediately get something that's uniform in the dimension.
Okay.
Further questions?
If you change the
I mean, in principle, the way the proof is done, you should think of M really as a function that splits the product F times G into large and small values. So it's naturally traced on R. I mean, the problem itself makes sense in higher dimensions, but to be honest, we never really looked at a higher dimensional version of this problem. You will see that in 1D, it's already not too easy to solve. But in principle, it would make sense then of course you have to check what the right powers are to sort of balance everything to really give you a finite constant. Okay, good. Then let me make some space. Of course, I won't have time to go through all the details, but let me just highlight a few of the nicer features. One remark, let me make that here, that bound here is extremely robust in the sense that the proof easily generalizes, and most of the times with the same constant, to situations where maybe you don't look at minus Laplace, but you look at minus Laplace to some power sigma, say, so polyharmonic Schrödinger operators, or maybe even to general kinetic energy symbols, T of P. Under natural assumptions, you can basically get the bound whenever you can hope for a bound. So that depends on the zero set of the function T. You can also generalize to V's that are not real valued, but operator valued. So you can think of situations where V maps RD maybe to something like C2, or in general, a Hilbert space. Oh, sorry, what am I saying? Yes, that's also possible, but what I want to say is taking values in the space of operators on a Hilbert space, say in L2 of something, or more generally in Schatten class of order d over 2 of potentials. And then you can generalize even further and get a full statement a la Cwikel's theorem, which gives you conditions under which if f is in some LP space, G in some weak LP space, when this operator product is in a weak trace ideal. But let me not delve into too many abstract things here and really stick to the simple situation of minus Laplace plus a real valued potential where we have this bound here. Okay, I hinted at this maybe surprising connection that this variational problem also appears in a recent bound on the Lieb-Thirring constant. That is due to Rupert Frank, Dirk Hundertmark, Michael Jex, and Fantan Nam from 2021, I think, which says that, let me just state it a bit sloppily, if you now, instead of looking at the number of negative eigenvalues, you look at the sum of negative eigenvalues, then you can also bound this by sort of the semi-classical guess, which would be the negative part of the potential to the power 1 plus d over 2. With a constant, let me call it L1d for Lieb-Thirring constant. And what they proved is that this L1d can again be bounded by something that is expressed in terms of variational problem. And this variational problem, we were actually able to reformulate into exactly our M gamma here. So again, if you factor out the classical constant from the classical guess, which I don't want to write down now, then this is again bounded by some dimensional factors, p plus 2 over 2, gamma minus 2, gamma minus 4 over 2 times M gamma, where now gamma is 2 plus the dimension. So again, a related but still different question on the energies and bound states of quantum systems, this variational problem again appears with the corresponding parameter, which is natural in view of the bound. I actually haven't checked whether one can use the methods, combine them, and get bounds on higher powers of so Ried sums of the negative eigenvalues, but I would not be surprised if one found a similar estimate that again involves this variational problem M gamma for corresponding gamma. And by solving this variational problem, one can actually again get slightly better bounds than Rupert and colleagues got by just using some surprisingly good choice of test functions. So we are only slightly better. So they did a good job in guessing a very good function. But in fact, the guess was very good. Okay, good. So let me, in the second part, tell you a little bit about how to solve the variation problem. And it actually has two sort of main features, namely, first of all, a nice rewriting of the problem where you see the convexity. I mean, if you look at this variational problem and I would tell you prove that it's convex, good luck. But there's actually a nice way of viewing this problem which reveals its convexity. And once you have a convex variational problem, you have all the machinery of duality at your hand. So one can reformulate it using convex duality, so Fenkel-Rockefeller duality, and derive a problem which funnily looks very much like a question, classical question from interpolation theory, namely the Hadamard 3-lines lemma, which is sort of the main tool improving interpolation results. That somehow appears here, but in a slightly twisted form. And the second feature is that, okay, I mean, you want to say something about a non-local operation of two functions, and we will see in a second that this has a lot to do with questions about the Fourier transform. And you want to compare it with an exponential. So it naturally somehow led to study analytic extensions of functions. And since we talked about complex analysis over lunch, I mean, that's really where some basic complex analysis tools can be used, like residue theorem, to get a very good understanding of the problem. So let's see. The starting point basically of the talk, if you like, is a very basic observation, which, however, has a sort of very deep consequence in what's coming next, namely about the Fourier transform of L1. And now that is again where this new point of view comes in between convolutions and Fourier transform, namely that if you take your favorite distribution M on R, then what you know is that, say, the inverse Fourier transform of this distribution, which is again a tempered distribution, but this is actually in L1, if and only if you can find two functions, M1 and M2 in L2 of R, such that M is the convolution of the two functions. And you know even more, namely, you can calculate the L1 norm of this inverse Fourier transform by taking the product of the L2 norms of such a splitting and just minimizing over all choices of M1 and M2 such that M1 and M2 represent M by convolution. But that is nice because this allows us to reformulate the first part of this problem in a way that involves the inverse Fourier transform and gets rid of the convolution. So with this, and the proof is really just a few lines, so maybe I leave it as an exercise, you can rewrite m gamma as the infimum now over all functions m such that, say, its inverse Fourier transform is in L1. The product of the two L2 functions becomes the L1 norm to the gamma minus 2 of the inverse Fourier transform times m minus the exponential in this weighted, exponentially weighted space. And then, okay, let me, in order not to worry too much about the inverse Fourier transform, let me just reparameterize and infimize over all m in L1, the L1 norm to the gamma minus 2 of m times m hat minus the exponential function L2 gamma squared. And here you really see, and let me call this function here, maybe now I'm running out of space. I hope online, yeah, online you can still see it. Let me call this function now here f gamma of m. And let me make two observations. Clearly, this function f gamma, which takes an L1 function as an input and spits out something in R, maybe plus infinity, that's this exponentially weighted L2 norm squared, but it's manifestly strictly convex. Maybe I should use a different pen. So that's strictly convex. And it's also easy to see that it's lower semi-continuous. So there you really have your machinery of convex analysis at hand. And you can calculate its domain, namely all the m's in L1 for which is finite. And that is nothing else than the set of all m's such that the Fourier transform is has bounded distance from the exponential in this exponentially weighted sense. Okay, now this, as I said, opens the door to perspective 1, which is convex duality. More precisely, by a simple scaling argument, you can see that m gamma is actually the infimum over all functions m with L1 norm less or equal 1 of f gamma of m. So you really have a strictly convex functional that you are minimizing over a convex set. Very good. And let me maybe write this a little bit differently. Let me minimize over all m in L1 and sort of add a hard constraint, g of m, which is the indicator function of that set in the sense of convex analysis. So that function here is plus infinity if m, let me write 0 if the L1 norm of m is less or equal 1, plus infinity otherwise. Then by the celebrated Fenchel-Rockefeller duality theorem, you can also see this problem, or this problem is equivalent to the supremum, which actually under very mild assumptions turns into maximum. So for the dual problem, you automatically get existence of an optimizer. over all G, say, in the dual space, which is L infinity, and then minus F gamma, the dual, so the Legendre-Fenchel dual of your functional of G minus G star of minus G, where G star, the dual of this function, is just the indicator function of, just turns out to be the L infinity norm. So that's one aspect that I don't want to dwell any further on. Let me go to the second aspect, namely this feature that we somehow want to see how close a function m, or the Fourier transform of a function L1, can be to an exponential in this exponentially weighted sense. Ah, yes. Okay. So star. Very good. So F gamma star would be a functional on the dual space. Again, taking values in the extended real line, and is defined by, say, of G is defined as the supremum over all M in L1. And now you take the dual pairing between L infinity and L1, which, since I'm working with complex valued functions here in general, let me take the real part of the integral of G of x bar M of x minus F gamma of M. And the funny thing is that this you can actually calculate this explicitly for this functional F gamma. Maybe I can give you a few more details a bit later, but it's really what you know from classical one-dimensional convex analysis as a Legendre transform of the function. So you see, very elementary methods, but you sort of need the right combination of them to get your hands on this variational problem, which I found quite remarkable because it's a variational problem of a type that I've never seen before. And you really need to work hard to get anything. Further questions? Okay.
So
yes.
So how come the original problem is not convex, and when you write it in terms of Fourier transform, it becomes convex? So there is something that I don't understand.
No, it is, but you're just sort of looking at it in the wrong parameterization, I would say.
Oh.
And by really writing this in a sort of simpler way in that sense, because you eliminate the two functions into one. Of course, that comes at a cost. I mean, you don't lose this non-locality from the Fourier transform, from the convolution, because now you have the non-locality from the Fourier transform. But it somehow allows you to much easier see that it's a convex variational problem.
Okay.
If you know optimal transport, and so sort of, okay, I should have said, I mean, in principle, my business is optimal transport and its regularity theory. So that, again, sort of was a nice side project. In optimal transport, you have a similar situation. In optimal transport, you have a variational problem, which is minimizing that sort of very far side remark that I will remove in a second. In the sort of most flexible formulation of optimal transport, you sort of want to minimize the cost, the total cost between coupling particles described by a probability distribution, say mu and 1 nu. So you minimize over couplings, that is probability measures on the product space with the right marginals. Let me just call it couplings between mu and nu of the cost that it takes for particle X to be moved to position Y with respect to the coupling, say, on RD cross RD. That is a linear variational problem on a convex set. However, it has a hidden strict convexity that in this parameterization you don't see. You see it, for instance, when you turn to the Benamou-Guinier, so to the dynamic formulation, which says that equivalently, you can view this as a minimization over densities and fluxes. You look at the kinetic energy or the kinetic action. So RD and 0, 1, 1 over rho J squared over all flows that connect the two measures. So dt rho plus the divergence of J is equal to 0. Rho at time t is 0 is mu. Rho at time t is 1 is nu. And there you have your strict convexity, because the map that takes a rho and J and maps it to 1 over rho J squared, that is jointly strictly convex in both variables. And that's, I would say, morally a similar thing. So you have your variational problem, but you parameterize it in a sort of obscure way that doesn't work out the strict convexity. And that's one of the reasons, so that's really what got us started. That's one of the reasons why in the original paper we couldn't solve it, because we just didn't see this convexity. That is relatively classical, but you can prove it in 3 lines. You can find it in Rudin's book on Fourier analysis on groups without the norm characterization here, but that's also just a simple outcome. Okay, so a very long story about this strict convexity, but I think conceptually that's really an important thing, because that got us really started and made us understand in the end what's going on. And the second thing is, again, this perspective here that we want to work in spaces of say holomorphic functions, holomorphic in the sense that at least you can extend your functions holomorphically to a strip, because that's where exponentials somehow have the Fourier transform. So you really need this extension to the complex plane to be able to see the interplay between the exponential function, which is not in L1, and this Fourier transform here of this L1 function. Okay, I should take 10. In order to see what's going on, and let me maybe do this because that's quite instructive. Let me first do a small normalization. Let me factor out this gamma, which is a bit annoying. So let me introduce m tilde of x as gamma over 2 m gamma over 2x. Then the Fourier transform of m hat tilde of k is just the original Fourier transform of m at the scaled argument. And with that, you can reformulate the problem as the infimum over all m tilde, say, in L1. You take the L1 norm of m tilde to the gamma minus 2, but there you have to be careful, because there you get an extra factor, and together with the L2 norm, which you also see, you actually get a 2 over gamma m tilde hat minus the exponential, and the exponential now of course sees the scaling. It's going to turn into a exponential 2 over gamma, but now in a space which is weighted only by an e to the minus 2x. So this exponential here, this is just e to the 2 over gamma x. That normalization is somehow nice because it allows us to really work with the space of functions in the complex plane that extend to a strip of a fixed width. But of course, now you have the dependence on gamma here in this function. And the next observation is that if it weren't for this exponential, so if you had an exponentially decaying function to both sides with this 2 over gamma exponent here, well, then you can just write down the Fourier transform, and that is just the function p gamma of x is 1 over pi 2 over gamma, so your favorite Cauchy distribution, plus x squared. Then this function here has Fourier transform given by e to the minus 2 over gamma modulus of k. That is our friend. But as you will see, or as you see directly, if you extend this function to the complex plane, it's not holomorphic, but it's meromorphic with two poles, the one sitting at I2 over gamma and the other one is at minus I2 over gamma. And the goal will essentially be in sort of, in some sense, approximating this function here, or at least the poles of this function, or one of the poles of this function, by a good enough holomorphic function, or by a good enough meromorphic function that sort of models this pole in a good way, in this weighted L2 sense. Okay, that's maybe a bit too much for to digest without seeing what I want to do. So let me now use this function here and just look at p gamma hat minus this exponential 2 over gamma in L2. Well, what is this? This is the integral over R of p gamma hat of k minus this exponential. Well, the good thing is half of the exponential is eaten up. So what's left is just the integral from 0 to infinity. And then here we have a e to the 2 over gamma k minus 2 over gamma k minus e to the 2 over gamma k squared. And that comes weighted with an e to the minus 2k dk. But since gamma was always assumed to be bigger than 2, but the first part is for sure integrable, this part here, which is exponentially growing, is actually compensated by this decay here. So this guy is finite for any gamma bigger than 2. So we can just use it and look in the variational problem for deviations around this fixed function p gamma hat. Or in other words, we can think of the domain of this functional f gamma also in terms of the functions m in L1, such that m tilde hat minus exponential 2 over gamma is in L2 as the set of all m in L1, such that m tilde is the sum of this p gamma and a deviation v, which will not anymore have a problem because of these poles in the complex plane, but of course has to satisfy that v is in L1 with a Fourier transform in this weighted, exponentially weighted L2 space. And with that, you can reformulate. You see, it's lots of reformulations, but really reformulations where you learn something about the problem. As 2 over gamma times the infimum now over all v in L1, such that v hat is in this exponentially weighted L2 space. You have the p gamma plus v, L1 norm to the gamma minus 2. And now you took out sort of the p gamma here. So you have a p gamma hat plus v hat minus the exponential 2 over gamma in this weighted L2 space. So you just parameterize m tilde as p gamma, and for that it was important for p gamma to be actually admissible. Okay. Now, as I said, this function p gamma extends in an easy way to the complex plane. So let me introduce the function p of z just as the 1 over pi, 2 over gamma squared plus z squared. Then in the complex plane, this function here has two poles, but is otherwise benign. And we can look at its value sort of at y is equal to 0. So with this, and that's then a function of x, I just mean p of x plus I 0. And that's nothing else than p gamma of x. Now, let me also introduce the trace at 1 as the function p of x plus I. That's that. And let me have a look at what the Fourier transform of this function is. Of course, by looking at the Fourier transform shifting in the complex plane, that will produce exponential terms. So the Fourier transform of P1, so the integral, and let me normalize the Fourier transform in that way. So let me take it with a minus here, but without the 1 over 2 pi to the d. So 1 over square root of 2 pi dx. Then I can do a contour argument, and instead of integrating here, deform to the integration here. But of course, you pick up a residue. And what is the residue? So, okay, if you move the integration down here, then you move the exponential by minus I. But that picks up an exponential term, so p0 hat of k e to the minus k plus or minus 2 pi I times the residue, because you're sort of going the wrong way, at I2 over gamma of this function p gamma e to the minus I kz. But shifted by I. And that, okay, I spare you the calculation that you can do, and you get a p hat of 0k e to the minus k minus an e to the 2 over gamma k e to the minus k. But that's interesting now. Sorry, I should move back over here. Let me write the conclusion quickly here. That tells us that P0 hat of k is related to P1 hat k by an exponentially growing factor, namely P0 hat of k is P1 hat of k times e to the k plus e to the 2 over gamma k. But now you see what happens. Let's see, what did I do? I solved for the P0 hat of k, and for that I multiplied by e to the k. Yeah. Because that's what we have here. So this is the P0 hat of k. So by going from P0 to P1, I magically take out this exponential here. So this guy here is nothing else than the P1 hat with the exponential plus V hat, but this exponential here goes away. Now this is a weighted L2 norm squared. So if I take the square of this guy here, I get an e to the 2k, but that's eaten up by the e to the minus 2k from the definition of the norm. So I can also write this as a P1 hat plus V hat, but okay, the V hat then pays the price. It's multiplied by an exponential, which is now e to the minus k. Now things would be very nice if I could somehow put this again using Plancherel into real space. And again, think of this calculation now. In this calculation, we basically just shifted the integration in the complex plane. Well, here we picked up something from the pole. If I take the V to be holomorphic, I don't pick up anything. So if I can realize this guy here as the Fourier transform of a shifted function into the complex plane, which is holomorphic, then I can write this just as, let me put this with a question mark, as a P1 hat plus a V1 hat in L2 norm squared.
Yes.
And that's now the second point, and then I think I have to finish. That motivates the definition of functions in the complex plane that are holomorphic on a strip, admit boundary values at y is equal to 1 and y is equal to 0. Automatically, if they're holomorphic, they will be related. The Fourier transforms will be related in this way, such that they minimize a variational problem, which now, since I can write this as 2 pi times P1 plus V1 L2 squared, got rid of the Fourier transform at the price that I sort of now have to extend my functions to the complex plane. But that is actually the core trick. And maybe I just use the last minute. It wants to be, but it can't be just quite. Because you also have this constraint here. And remember that the V here has to be a function that extends holomorphically to the strip, so it cannot be P gamma because it cannot model the singularity. So you somehow want the best holomorphic approximation of P gamma in this sense with
the holomorphic part of the meromorphic function. That in the Lorentz series, you want to take everything with the
in principle, yes. In principle, yes. And our way of rephrasing it is sort of because it's, I mean, you still have to treat this L1 term here. So it's not clear if you do that you actually solve the variational problem. Because it's really sensitive towards the remainder. And but that is now going a bit too far. Let me maybe just quickly write down here one of the main insights in form of a theorem. Part one is you can reformulate now using this convex duality side, this variational problem. Let me write just a C gamma here because it's not important, as a maximization problem over functions which are in a space that we called H infinity 2 of S minus. So they are holomorphic functions on the open strip from -1 to 0, which admit boundary values in L infinity at 0 and in L2 at -1. So the picture is the following. Here I have my complex plane. Here I have y is equal to 0, y is equal to -1. And I want my function to have a boundary value which is in L infinity here and in L2 here. And we can actually prove that this space that we introduce, and I don't want to bother you with details, admits these boundary values in a distributional sense. And now you take the L infinity norm of H, of this function H, which is holomorphic in the strip, at -2 over gamma. Gamma was bigger than 2, so that's somewhere a line here. And divide by the L infinity norm to the power gamma -2 of the trace at 0, and at -1, the L2 norm to the power 2. Which, if you remember Hadamard's 3-line lemma, is essentially that with the lower norm here replaced by an L2 norm. So Hadamard would tell you if you know the function is in L infinity here and L infinity here, that you can control it in L infinity in between. Here it's somehow what happens if you control it in L2 and in L infinity, can you bound it in L infinity here? And the answer is yes, and you can even calculate the maximizing function here. And this turns out, so the maximizer is of the form p gamma of z e to the I theta gamma z. Well, that doesn't tell you much, where p gamma is a so-called Blaschke factor, z minus z gamma divided by z minus z gamma bar, with z gamma is I times 2 minus 2 over gamma, is a number in the upper half plane. And that's sort of the part that takes care of the pole. And every other information is in the phase, and this phase you can calculate explicitly as a sort of inverse distributional Fourier transform of a function, and the distributional character comes in the sense that you have to sort of calculate Cauchy principal value, but now a sort of third order principal value. So you have a function that is explicit, that comes in principle from the phases of this Blaschke product, e to the minus ikx, ikz, and then you take out sort of the first order. And the reason why you have to take it out is because you divide by something that has a third order divergence in the denominator. And this function g, I could write it down. It has to do with arctangents, Fourier transform of arctangents, but let me maybe stop here. So in this sense, you can explicitly solve the problem. You could now sort of revert by duality back to what M is, but that's a nasty formula. Let me maybe leave it here. So you have this very nice connection to a 3 lines lemma type problem, but with a much harder structure. I mean, for the 3 lines lemma, you can basically write down by a maximum principle what the maximizer has to be. But here you can't. I mean, you can also, but it's much more complicated. Okay, sorry for going a bit over time. Let me maybe stop here. Ah, very good.
Thanks to Tobias for the excellent presentation. You can say it.
So you already have a preprint, or you published your second paper?
The preprint is online, yes. It actually appeared 2 weeks ago or 3 weeks ago, so it's the first time I got the opportunity to talk about that. And in principle, it's just a series of, as I showed you, a series of rewritings, but with each rewriting, you understand more of the problem. And I think that's why it's really nice to go through it on the blackboard, because you can really sort of see how it develops and what kind of then advanced techniques you have to use. And it's really this characterization of Fourier transform of L1 combined with the duality, but then you still have to study spaces which are a bit like Hardy spaces in the upper plane, but you sort of have to do Hardy spaces for a strip, because you need access to 2 types of boundary values, only the ones at 0 and the ones at 1. And then essentially you solve the Euler-Lagrange equation, which relates value at 0 with the value at -2, essentially. So there you see the non-locality. And with this ansatz here, you first linearize it, because it involves somehow the sign of the function here is a constant multiple of the function down here. So you somehow linearize it by taking out exactly the factor here that takes care of the singularity, and get an equation which is now linear but still non-local in the phase. And this phase you can explicitly solve with such a singular integral ansatz. So essentially, you really, I mean, then you sort of have to solve a distributional inverse Fourier transform problem, but you can write it down explicitly, and it's mild in the sense that you need a Fourier transform of an arctangent or so, which is still a nice distribution.
Also very nice, but does it give you in any sense, because finally what you are interested in is the constant in the Cwikel-Lieb.
Exactly, exactly.
Does it give you some chance to have something optimal, or think it's
The answer is unfortunately negative in the sense that now that we can calculate this m gamma explicitly, we know that with our method, we can at most go down to 7.51 something. So we are still a good bit above Lieb's constant in 3 dimensions.
no in 3 dimensions? Yeah,
In 5 dimensions and higher, you can improve a little bit on what we had before.
but it is, let's say, no, I don't know, in the limit, something approaching optimal or something like that.
Unfortunately, also not. But that also has to do with the fact that if you take Cwikel-Lieb-Rozenblum and sort of take the limit d to infinity, then it's not really known what should happen. But we can sort of calculate the limits in Lieb-Thirring and in Cwikel-Lieb-Rozenblum explicitly.
So define the Cwikel method.
Exactly, yeah. And that led to this variational problem that I would say, I mean, the preprint for the Cwikel-Lieb-Rozenblum paper came out 2018, so it took us almost 4 years to solve it, after already working 5 years on the other paper. So
Question or comment? Anyone from the people online? Any question? Before to say thanks again to Professor Tobias, I have 2 announcements. The first one is this week you have another seminar, is Wednesday at the same hour. We hope without not late. And the next week we have the 34 Jornada de Matemática de la Zona Sul, de la Universidad Católica de Temuco. Then you are invited to be there. And and sorry to take you away from rest. And let's say thanks again.
thank you.
Thank you.